Okay, so this week the prodigal son returns again. We welcome back Laurent Cantier to tell us about continuous fields of interval algebras.
Okay, thank you for having me here, and thank you for the introduction. Yeah, it's been a while, but it's good to be back. And I will speak about some work in progress. So some hopefully I will talk only about things that I've proven so far, and it's about continuous field of certain system algebra. So will namely be interesting in interval algebra. So I know some people are not especially about system algebra, so I will try to recall some some of these algebra. So a bit of motivation before we start. So the motivation comes from the fact that in the 60s, 50s, 60s, so classification of AF algebra. So the F stand for finite dimensional, and we take inductive limits of such algebra. For those who really never study system algebra, finite dimensional system algebra are just matrices or direct sum of matrices over the complex number, and we take inductive limits of those. And so mainly I should state those two protagonists. So in the 50s, 60s, they classify AF algebra with some K0 data, which is mostly looking at projection of your algebra. And so based on this classification, in 2011, so Gadala, Elliott, and New were able to somehow use this classification to classify continuous field whose fiber are AF algebras. Okay. So continuous field over the interval. I will define all those terms. Whose fibers are some AF algebras by some extended K0 data. Okay. So knowing this and knowing the fact that the Kuhn-Semi group, so I will not define what the Kuhn-Semi group is, but one can think of extension of K0. Instead of looking at projection, we look at positive elements. I will not talk much about the Kuhn-Semi group for once. So it has been proved between 2008 and 2012, roughly. So I will recall later the specific theorems, but yeah, let's say three main results. That the data encoded by the Kuhn-Semi group allows for classification of what's called AI algebra. Okay. Of K0 or positive elements. So this is a complete invariant for AI algebras. So the AI algebras, in particular, AF algebras are AI algebras. So the I now stands for interval. So we look at matrices over the continuous function over the interval. We take building blocks and we take inductive limits of such sister algebras, okay? So the question is, can we extend this result to certain continuous field of sister algebra? Okay, so obviously we will have some restriction on the base space, probably some restriction also on how the field looks like. I will get into detail of such things. So I guess I've introduced a lot of words that might not be familiar for some of you. So I'm not really interested in the invariant themselves, but more on how can one extend a local classification to a global classification of the entire continuous field, okay? So that's why if you don't know what the Kunsemi group or the Casey group is, you should be fine. So the first thing to do is to properly define what is a continuous field of sister algebra. In the literature, there's been several equivalent pictures. Sometimes it's quite hard to track what someone means by continuous field. For my side, I will take the definition that was introduced by May Nielsen in the 90s, and we will start from there, okay? So a continuous field of sister algebra, you should think of maybe like a vector bundle. So you have a base space, which is a topological space, and the fibers will be sister algebra that varies continuously in a certain fashion, no? So a continuous field of sister algebra for me will be a triple. So we have a topological space which for the talk will be compact, Hausdorff, and in fact of dimension at most one. We have a family of sister algebra which will be the fibers, and this family is indexed over the point of the topological space. And we have another global space which is also a sister algebra, and so I will precise all of this. So X is a compact Hausdorff space. Those AX is a family of sister algebra. Indexed by the space. And A, for now, is just a family of what one can call a section. So a section, there are two ways to picture a section. It's either an assignment from X to the disjoint union of the fiber, such that each image of X is an element of the fiber, or you can just picture as an element of the product of the fiber. Okay, so it's that AX belong to AX, or similarly, you can think of as a an element of the product of the fiber. So basically, you just assign a collection of points in each fiber, okay? And now I want this curly A to be a family of section, to behave to behave nicely so that it actually describe my continuous field. Okay, so the first thing I want to have is that this global space is a C-star algebra. Under the pointwise operation and the supremum norm. So I can sum, I can multiply just fiber-wise all those guys. I can look at the norm, which is the sup norm and so on. I want to ensure that I have enough of those sections. So for every x, I have this evaluation at point x. So I will call it pi x is a map from the curly A to one fiber. And basically you just evaluate your field of element to the point X, and I want this map to be subjective, okay? And it has to be a surjective star homomorphism. Now I want a third property that will allow the section to be well behaved. So basically, namely, I want that for any section in my curly A, then map that to a point X sends the norm of AX. This map is continuous. Okay, so 2 is I have enough section, and 3 they are well behaved. Okay, and a fourth condition is I want stability by C of X multiplication. Okay. Okay, so once I have this, there are other picture of these things. For example, maybe you've heard about C of X algebra, and in the case where X is nice like that, and we have those maps are continuous, those are equivalent pictures, okay? For, yes.
So the last point means that like if I multiply with a continuous function, then I see.
Yeah, it would be the pointwise multiplication. So you take a function and you just any of those maps, you just define f times a to be the map that sends x to f of x times a of x. Okay, and this has to belong to the curly a again. Okay. So this defines a continuous field of C-star algebra, and actually there was a picture that, as I was saying, and in this picture, the nice thing is that this curly A can define a topology on the disjoint union of the fiber. Okay. And this topology will be adequate in the sense that if you give me such a section, the continuity will be a characterization of belonging to curly A. Okay, so this is the kind of characterization we want to get at. There is an adequate topology of A. And this topology, we can have an explicit description. It will be generated by the basis of open sets of the form here. So the topology to A on So disjoint union of the fiber. And so we will look at a point in any of the fiber has to be so the fiber has to, so I will explain all those things, but V is an open set of X, A is a member of curly A, and epsilon is arbitrary precision. And so the open set will be all those points in all of the fibers such that, so first of all, I want the fiber to be in the open set that I chose, and that this section, which I know belong to my global space, passes close to this point, okay? And okay, so V is an open set of X, epsilon is an arbitrary precision, and A is a section in my curly space. Okay, so basically, I choose a point in any of the C-star algebra, which are my fibers. And if for any precision I can find a section of my global space that's approximated as close as I want, okay, then I will say that this point belongs to this open set. And then I generate topology based on those open sets. And we have the following nice characterization. So now, because the point of this topology is to know when an arbitrary section belongs to actually curly A, okay? Because curly A, somehow you can picture it as a subset of this thing, okay? Or a subset of section. So, yes.
So you're saying that VAE is the set of all those sections such that for all little v, this norm.
No, it's not a set of sections, it's a set of points. So A sub V belongs to the disjoint union, yeah? So this is X, you have all the fibers, okay? And so you choose an open set and you look at all the points in any of the fibers that are based at V. So
Like little open tube.
yeah, kind of. So I choose one point, and if I can find some section that approximated up to any precision, then I say that this is in this open set, okay? So I really have two types of objects. The first one are those sections, and the second ones are points in what, like a given fiber, okay? And so you get, yeah, kind of a tube around this point, something like that, okay? And so the point is to really characterize, if you give me a field of elements, so a section, when to know if this section belongs to your global C-star algebra or not, okay? And it will be exactly when it's continuous with respect with that topology. Okay, so let's so I take a section, okay? So it's a collection of points indexed by my topological space, yes? Then I do have this characterization that if I call this element A is in curly A if and only if A is continuous with respect to the topology I just generated on the disjoint union, okay? So it's kind of getting back more like yeah. topological viewpoint on those continuous field. Okay, so all of these are more or less well known, I would think. Yeah, it's not always super clear how in the literature those things are articulated together, but I've checked the proofs and it's fine. But mostly what I wanted to get at is to get something similar for what I will call continuous field morphism, okay? So because I'm aiming for some classification, I need to know what's going on at level of category theory. So I have my objects, which are those continuous field of sister algebra, and I want to make precise what is a morphism between two of those objects, okay? So, yeah, probably from now on, all continuous field are continuous field over the same space X, which is compact Hausdorff of dimension at most one, over the same space X, which is compact Hausdorff and of dimension at most one, okay? And so to his notation, I will just refer to continuous field as curly A, curly B, when I really mean that this triple, okay? The fact that I choose to always have the same base space is probably to get things done more easily, but surely you can try to think in the future at morphism between continuous fields that are not over the same base space. Okay, so I have two continuous fields over X. A continuous field morphism between those two things. So in particular, curly A and curly B are sister algebra. Okay, this is kind of my global space. So a continuous field morphism will be, in particular, a star homomorphism with some extra property. Okay, so I really do want a star homomorphism between those two family of sections, which are sister algebra. And I want them to behave well with respect to the fibers, okay? So we will say that it's a star homomorphism descending to the fiber. Meaning that it induces a collection of star homomorphism between the fiber of A at point X to the fiber of B at the same point X. Okay, so that's why I choose to all my continuous field over the same base space, so that those things are easier to introduce. Phi induces family of star homes which is also indexed by the point of my topological space. Okay, I should precise that phi x go from the fiber x of A to the fiber x of B. And I want a compatibility, obviously, that the following square is commutative, okay? So remember, those maps are those surjective maps that I defined earlier, and I want this to be commutative, okay? So in particular, there are star homomorphism, but even more, they satisfy an extra property. Yeah. What do you mean? Which satisfies this thing? That's why I choose this picture and not like another picture. Exactly. So that's why I wanted to. Yes, you need to prove it is true, but you will need to prove it. But I will not speak about C of X algebra. I will really just use those definitions for what I aim to do.
Oh, so this back to this, but there is an adequate topology. So adequate means that what any continuous section with respect to that topology is actually in A. Is that
Yeah.
what adequate means?
Yes.
Okay.
Yes, that's what I mean by adequate. Like,
So sometimes they would just call these C-star bundles, right?
yes, it's also a third picture of it. Yeah. But the C-star bundle, for example, they don't specify. They just speak about two topological spaces with a projection map such that the inverse image of each point is a C-star algebra with some other condition. So that's why there are many different objects that overall are, I guess, equivalent categories. But many times the morphism are not so clear what it is and so on. So I thought it would be good to make a recap. Yeah, there are C-star bundles. Because X is compact, Hausdorff, nice dimension, and so on. But the point of taking this picture is that I would like to have something similar for if you give me a family of star home from AX to BX for all X, I would like to know when this family is in fact a continuous field morphism. Okay, this is far from being true in the general case, and we need this kind of continuity with respect to which topology. I will make this precise. So the question is, when is a family of star home, when it is a family a continuous field morphism? Okay. So what I will do is I will kind of mimic this construction to define a topology on the disjoint union of the set of star home between AX and BX. And this topology, so I will need an extra assumption, but will give me kind of the same proposition as I had for elements. Okay. So probably some notation. FC star now is the category of continuous field of C star algebra together with the morphism. Okay. So we construct okay, so this name I chose it, maybe it's not the best name. A home bundle topology. Now A to B. No, it could be multiple X, but just from what I have defined, if you have two continuous fields over a different space, the set of morphism is empty. which is
Is what, sir?
empty. If
Yeah.
yeah, otherwise you would need to define something that is more general. Probably you need a map. Like I think you need a proper map from X to Y, which X and Y are the base space, so that you can make things work out. I don't know. I haven't looked so much in those things.
There were these morphisms defined by the guy Varela, where you'd have a map in one direction of the spaces and a map in the opposite direction on the bundles, and you would combine them to get a map of the corresponding section.
Yeah, I guess that could work. But I think you need like the map from the base space has to have some characteristic. You cannot take any continuous any map from X to Y. I think you just no.
Yeah. I think continuous problem, but it needs to fit well with the map on the total spacing as well.
Okay.
Yeah.
But I thought you needed like some properness or something like that.
Yeah, definitely proper as well on the base space.
Yeah. Yeah. Then yeah. Fair enough. Yep. But for me, yeah, two different base space, continuous field, no morphism between them. So it's easier. So this topology on the disjoint union of these things, okay? So what's going to be hard to get this equivalence is that now those things, they have way less structure, okay? So, for example, it's not even a vectorial space. But still, I will define in a similar way. I will use the element that I know that are continuous field morphism, and try to see to define some basis of topology in the same fashion that I have. If you fix one element in one of the fibers, so a star home, I want that there is up to any arbitrary precision a continuous field morphism that pass close by, okay? And there are the forms, so V, phi, F epsilon. So those are really a star homomorphism between any two fibers, such that, so I want that where this happens belongs to the open set V that I have chosen. And I want that psi, okay, psi of psi V is closed on FV up to epsilon to phi V. Okay, I need to define some notation. So first of all, V is again an open set of X. F is a finite set of section in curly A. Epsilon is an arbitrary precision. And Xi is a continuous field morphism between A and B, okay? And what I mean by that, I mean that two-star homomorphism are close to up to an epsilon on a finite set if the image of any element is, the differences is close by an epsilon, okay? And Xi V IV means that psi V of AV minus phi V of AV okay? So the finite set A, when I project it down to the fiber, it gives me finite element of A sub V, and I looked at the two-star homomorphism, which are from AV to BV, are closed on this finite set up to an epsilon. Okay, this is what I'm saying. So you can picture it, kind of this thing that's going on. Okay, and now one would intuit that hopefully I get the same proposition as I had for the element of my continuous field. And yeah, because these things has way less structure, it will not exactly happen like that. So given a family by x of star homes, consider the two statements. So one, the map phi from A, B, that to a continuous section sends the section defined as follow. Okay, so the most natural way you can think of is a well-defined continuous field morphism. Okay, so there are plenty of information here. The first thing is you can always look at this section, but maybe it will not even be in the continuous field B. Okay, so well-defined means that actually this section always falls into B, so it's continuous with respect to tau B, and plus phi, when I project it down onto any fiber, I recover phi x, okay? So this is what I mean by well-defined continuous morphism. And the second one, probably you've guessed what I'm about to write. The second one is that the assignment that sends to any x phi x is continuous with respect to the topology I've just defined. Okay. So what we will always have, what's always true is 1 imply 2. And for 2 imply 1, what I actually need, I just erased it, but it's kind of this subjective condition that I had in 2. Okay. So 1 implies 2. And the converse is true whenever I have kind of what I call projective property. Maybe it's not the base name. Projective property means that if I fix any star home between the fiber of A at point X to the fiber of B at point X, I can find a continuous field morphism whose projection down to this fiber is exactly or approximately would suffice the star homomorphism, okay? Meaning that for any star home between two fibers, there exists a continuous field morphism such that, okay, the projection of the continuous field onto the fiber V gives me back phi V, okay? So you can think of this as the condition 2 of the definition. For any element of the continuous field, I can find a continuous section that passes through that element, okay? So I want the same thing happen for morphism. I will comment on this condition, which is for now pretty restrictive, but still it allows me to have this continuity characterization for morphism. Okay, some remarks. Yes.
One that is a well-defined morphism. You mean that this function is in curly B?
Yes, this element is in curly B for any A. Yeah.
This I can be different for each point in the base space, right? Like for each V, it just says for each ID, there exists some chi, but this chi could be different depending on the point.
Yeah, I mean, even like the point V does not really matter. I just look at one fiber. I take one element, which is a star home, and I want that there is a chi that passes really close or exactly at the star home that I picked in the first place. Okay. But yeah. Even if you stay in the same fiber and you change the star home you started with, then the chi will be different.
Like, I can find something for each point on the base space, some continuous field morphism. Then I can find one continuous field morphism that works for all.
No, you don't. No. You just, so you have your X, and now each fiber is elements are star homes. Yes, between.
Right. No, I think I get what you mean, but I just mean like that's what the proposition is saying. That if I can do a point, then this phi gives me some global star.
No, so if you have this property, then 2 implies 1. So what I'm saying is that so this is a property, CP is a property of this set of elements. And now what I'm saying is that if you have indeed a star home at each fiber such that it's continuous with respect to this topology, then you know it's actually a continuous field morphism. But it's the same, you don't have to change it, okay? This is for later. All of this could work for compact Hausdorff space, but yeah.
Okay, so you have part of this, you have all these maps between the fibers, right?
Yeah.
So that would give you a map between the disjoint union of all the fibers. So and you already defined the topology on that before. Right. But,
yeah.
So what's wrong with just assuming that you have these maps and they're continuous with that topology?
This works, but nothing tells you that actually this assignment is continuous in the first place. If you choose random star homomorphisms, maybe when you take a continuous section of A and you construct a section of B, maybe this section is not continuous.
Right. But what I'm saying is that I would think, maybe it's even a theorem already, but whenever you have a continuous map between the fibers, which is continuous with the topology that you mentioned before, then that
yes, it is true. It is true. There are actually here there are like 3 or 4 points, and one of them is what you just mentioned.
Okay.
But I will not need them for later. So, but yeah, this is true. Yeah, I will come to this. For now, trivial fields. Beat. Yes, this works also. This is Blanchard result. Yeah. Yes, this is also true. But yeah, I will comment on that towards the end if time allows. But this is, for now, pretty restrictive. Yeah. Some remarks. So this topology, when I look at the restriction to, where is it? To one of those space, so to one fiber, it induces the point norm topology for those who knows a bit about star algebra. Okay. There's some natural condition on the base space and the fibers. This topology is metrizable. Okay. So since they are compact Hausdorff, it's enough to be, I mean, it's equivalent to be second countable. And all the fibers are separable C-star algebra. Then this topology is metrizable. Okay, we can even construct a metric D that induces the topology. And the restriction of D to the set of star home between two fibers makes it a complete space. Okay. Okay, this will be important. So from now on, let's say I restrict a bit more to X being of dimension 1. It's metrizable, and all my C-star algebras are separable. Okay. So I said I would try to extend this local classification result we have between the fibers to continuous field. So let me recall briefly the theorem. So probably it's overall the result of probably those three main results by Chuperka Elliott, Robert and Santiago, and Robert, that AB are AI algebras, so probably you need a unital. So what I can say is that any CU morphism alpha between their Kuhn semigroup can be linked to a star home, okay? And this lift is unique up to what we call unitary equivalence. Okay, I don't want to get too much into detail, but for those who don't know much about classification, this result is stronger than classifying C-star algebra. Okay, so in particular, if you have an isomorphism at level of the Kuhn semigroup, it leads uniquely to a star isomorphism. Okay, so the main attack now is to try to do the same for continuous field. Okay, so if I want to achieve something like that, there are two parts of the theorem. So the first is the existence of a lift, and then the uniqueness of such a lift. Okay. So first of all, remark that these curly A and B that I will consider are also C-star algebra, so I can look at their Kuhn semigroup. And obviously, it would be a bit foolish to try to lift just CU morphism between CU curly A and CU curly B. I need this kind of descending to the fiber condition so that I have any chance to lifted to a continuous field morphism. So definition. So we say that the CU morphism between this global space descend to the fiber if the same thing happened, okay? If alpha induces a family alpha x from CU of AX to CU of BX, such that, okay, when I go down, everything commutes. Okay, I don't have so much time, so yeah. So the goal is, if I consider now, from now on, my continuous field will be over one-dimensional spaces. All the fibers will be those interval algebra that we have this local classification result. And I want to goal, so for such alpha, I want to find phi, which is a continuous field morphism, such that, so I need two things. The first is, okay, that this continuous field morphism realizes my CU morphism, and it will be automatic that it descends to the fiber and alpha x agrees with phi x. Okay, this is not hard to check. And I want some kind of uniqueness up to the same unitary equivalence, because in particular they are star home. So I can consider this notion of star homomorphism. Okay, so to do so, probably I will keep this. To do so, I will present, so the uniqueness is quite technical, okay? And the main point is, I will comment if I have time, but what I really wanted to present was this existence part, so how to find this continuous field morphism that lifts my alpha. And so what we will do is we will use what's called selection theorems. So this part has kind of nothing to do with the rest, but we will kind of link everything together. So let me recall that yeah. So if I have X and Y that are topological spaces, a multi-valued mapping, multi-valued function is a map from X to the power set of Y, okay? So to any X, I assign a subset of Y. And we say that it is lower semi-continuous, and LSC for short, if for any open set of Y, the set of point X in X such that the image of X, which is a subset of Y, intersect non-empty with V, is open in X, okay? And lastly, we say that theta as a continuous selection if there exists a continuous map from X to Y such that phi X belongs to theta of X for any X, okay? So those are the main concepts to introduce those selection theorems. And So Michael worked a lot during the on those selection theorem, and yeah, he checked several settings on X, Y, the mappings theta, and so on, and yeah, probably. Yeah, I don't know if I have time to recall the theorem, but let me probably highlight the main strategy of how to use the selection theorem. Okay, so our goal is okay. So it guarantees the existence of continuous selections for lower semi-continuous maps theta, okay? Under, obviously, assumption on y on theta of x for any x, so it has to be so complete space. I mean, yeah, it's a bit technical, but I guess the main approach that I want to present is to solve this problem that I want to find this phi. For us, y will be the disjoint union on the set of morphism between the fiber together with this topology, okay? And now I know that I have my alpha, okay? And I know that alpha induces a family alpha x of star home. Okay, and now those alpha x are really satisfying the condition of classification. Okay, so alpha x is a C homomorphism between the Kuhn semigroup of two AI algebras or two interval algebras. Okay, so I know that they have a lift which is unique up to unitary equivalence. So we will consider theta alpha of x to be the element, so the star home between AX and BX that actually lift alpha x, okay? So in particular, any two elements in here are unitarily equivalent. So you can think of that they are connected through a unitary, okay? So in particular, this set will be a closed set of, so this is a subset of the set of star home between AX and BX, okay? We've seen that under separability, this was complete, okay, with respect to the metric. This will be closed because any two of those guys is approximately unitarily equivalent to each other. So this is a complete set, which was one of the conditions for the selection theorem. And okay, so there are technical stuff that I'm not saying, but there is another condition that has to be satisfied to apply the selection theorem. And the last thing is to check that now we consider the multivalued function theta alpha from x to power set of y to be at x, I look at these subsets of star homes, okay? So basically, I now want to find this continuous selection, and from the characterization that I had, this will give me a continuous map, okay? And this continuous map, I know that it exactly corresponds under this PP property to a continuous field morphism between A and B, okay? So theorem theta alpha is lower semi-continuous. Okay. whenever, so I need some restriction. So first of all is that I have the PP property. And A is locally trivial, okay? Is a locally trivial field. So, okay, it restricts the fields that I can classify. But as a corollary, as you asked me before, if A is actually a trivial field of interval algebra, it will be locally trivial, and the set of continuous field morphism from A to any continuous field B of interval algebra will have PP. Okay, so if A, so locally trivial means it's of the form C of X tensor A for some interval algebra. Then any alpha between CUN A and CUN B, okay, B doesn't have to be locally trivial or anything, lifts to a continuous field morphism phi between A and B. Okay? And this really uses this selection theorem. Okay? Basically, I lift all the alpha x to one of the star home given by the classification of AI algebra. I consider the set of all the admissible star homes. And by the selection theorem, I know that there is a correct selection that makes dispatching continuous. And we've seen that continuous means exactly being a continuous field morphism. Okay? And then there would be like this uniqueness part, okay, which does not involve all these selection theorem and so on. It's more like a brute force proof that you know that at each fiber, so you start with two continuous field morphisms such that they agree on the Kuhn semigroup of each fibers. So you know that there is a local unitary that links phi x to psi x. And what you want is to glue those unitary together in such a fashion that you obtain global unitary elements. So this is kind of like super technical and a bit boring, but it works. So this provides restriction on the field. And right now what I have, it provides restriction on the base space. So I have only been able to prove it for the interval, okay? So overall, if you want to retain a result, is that the information in the CU semigroup more or less classify inductive limits of continuous fields of the form C01 tensor AI by IJ. So this is a continuous field morphism, and this is an interval algebra, okay? So if I consider the class of those continuous field of C-star algebra, then by looking at the information that the Kuhn semigroup has, I'm able to, from the Roberts classification, to extend it to continuous field. Okay, sorry for overtime.
Do we have any questions? Me in person?
Maybe I missed this, but where are you using that X is dimension at most 1?
Yeah, I didn't say it. So the Michael selection theorem is true for dimension X. And so you need lower semi-continuity, you need completeness of all the images of your mapping. And you need a second condition, which is like kind of what's called equilocal connectedness. And for dimension n, I don't know what that means, but for dimension 1, it's easier to describe, and it means that if you have if you fix a radius epsilon and you take any 2 points in any of the subsets you have here, then you can find a uniform bound saying that if the 2 points are closed by a delta, then there is a continuous path of diameter, the radius epsilon, that connect them. And this delta has to be uniform on all the fibers. So this interpretation of this equilocal connectedness is for space of dimension 1. Otherwise, it's something way more complex, and I'm not a topologist, so I just didn't get into that. But it would be interesting.
So it's not it's like not a necessary restriction, just a.
No.
Yeah.
But yeah.
I mean, I guess you have to go do it. I'm just curious.
No, possibly it could be true for, but yeah.
I guess that's question you only care about the one-dimensional guys, but like everything is what the first limit of the, these sections of the bottom of the one-dimensional thing, I think, right?
I think you need to care about two-dimensional, maybe three-dimensional in full generality.
That's what everything in this things over one-dimensional. Everything that you guys like.
Okay, there's no simplicity stuff here, right?
No, there is not.
Yeah.
But even if you want simplicity, I mean, yeah, if you want something like torsion and K0, you need two-dimensional guys. Yeah.
Oh, like supplement, like.
Yeah.
Okay.
Yeah, you need.
All
right. Actually, so just following up on what you were talking about, this equi-LC thing. Like, okay, as you said, Michael worked a lot on these selection theorems, and the first one he worked on, the requirement on the function theta x was a convexity. You wanted these sets to be convex. And this is something you definitely don't have here because you're talking about sets of star homomorphisms.
Exactly,
there is no linear structure.
Yeah,
to it.
no.
So this is a replacement. This equi-LC
Yeah,
thing is
it's in the second paper that he has.
Yeah.
And it's more about complete spaces. So I think the original statement is that Y is a complete metric space. The subsets, the image of X, so each of the subsets are so closed, non-empty, so also complete, path connected. And you need also this equilocal connectedness, which is this uniform bound for all the subsets there. But you don't have to, theta of X need not be convex nor Y.
Yep.
So it's pretty nice because, yeah, set of star home, they don't have any structure.
And maybe just one final question. So you said you could do it for the interval. What do you think the prospects are for doing it for the circle?
So as far as existence is concerned, as long as you have projective property and local triviality, this is enough. So I don't have any restriction on the space X, a part that is dimension 1 at most 1. Yeah, for the uniqueness, my intuition is that the argument I have could work for the circle, but then, yeah, I feel like weird thing might happen in that case. So I need to check. I didn't have time so far.
Fair enough. Anything else?
Yeah, actually, I wanted to ask that. So what you meant with the interval is this theorem so far only holds if X is the interval? Is that what you were saying?
So the existence part, no, but the uniqueness part, yes.
Okay.
So the uniqueness part I didn't mention, but you don't start with an abstract CU morphism descending to the fiber. You just start with two continuous field morphism, and you assume that their projection on each fiber agree at the level of conserving group. So this gives you the unitaries that link them at fiber X, and you want to recover a global unitary.
This gluing these unitaries together.
Yeah, and this gluing right now, the way I'm doing it is I have this interval, so I have a beginning and an end, and I take this open cover and I stitch them from 0 to x1, and then from x prime 1, which is a bit before x1, to x2, and I just stitch them together like that.
Where you need local triviality.
Also, yeah. Yeah. Yes, probably.
And another question. So could you replace, so here you took a I algebra, like interval algebras and the Kunst semigroup, right? Could you just take, I don't know, classifiable C-star algebras and the Elliott invariant, and the argument still works with Michael's selection theorem and so on? Like how much does it depend on what invariant you have?
Yes, so this is actually a good question. Mm. The thing is that there are some things that I didn't say, but for example, this equilocal connectedness depends on the fact that they are really AI algebra. And there is a paper by Aristov, which gives you the path connectedness for free, which gives you this choice of the equilocal connectedness is free, is for free, is deduced from this kind of paper. So the invariant, the functorial invariant that I'm using, you're right, is not so relevant. But probably the C-star algebra that you have on the fiber need to satisfy certain property. And if you...
For this Y to be nice, basically.
For this Y to be nice, exactly, yeah, to apply the selection theorem.
Okay.
But, yeah.
Right, so there's nothing else. Let's thank Laurent again. And Stefan Wagner, who will talk about something that I can't read. There we go. Thank you so much. Spin structures in quantum geometry, a bundle theoretic approach. So hope you'll join us next week.